We're going to discuss how do you determine oxidation states of transition metals. That's the charge of the transition metal is in the compound. Let's take a look at these two transition metal compounds over here attached to nonmetals. You notice one is FeCl2 and the other one is FeCl3. Why is that? Why is there 3 chlorines in this one and only 2 in the other? And that's because the anion part of the compound was added so that it would balance out the positive part of the compound. And so there's a reason why there's a difference. One of the ways that you can determine what the charge is, the oxidation state is on the transition metal, is draw it. So I have iron and it's attached to 2 chlorines. Each chlorine has a -1 charge because I'm using my periodic table in order to read that column. When I add up the total charge in this negative part of the compound, it's a -2 charge. Now all compounds that we're writing are neutral. So iron had to have a charge to counterbalance that negative charge, so it had to have a +2 charge. Its oxidation state then is a +2. This is part of the process when you're naming any compound that has a transition metal in it, because you need to express what its oxidation state is when you're writing it, when you're naming it. All right, let's take a look at FeCl3. I'm going to draw iron with 3 chlorines in it, all right, because there's 3 of them in there. Each one of those are a -1. The total is a -3 charge. So this particular iron compound needed 3 chlorines in order to balance out the charge on iron. And the iron then would be a +3 charge. So when naming this compound, I would be naming it iron, and then in parentheses, I would be writing that it had a +3 oxidation state. And you write that as Roman numerals. Do not write iron with a number 3 behind it. It's Roman numerals. It's just the rules to follow. So let's take a look at these compounds over here. Now some students remember what it was like to write compounds when we were forming the formulas. They realized that at that time you would write the cation first and then the anion, and then you crisscross them and you would get a balanced compound. So when they're trying to do the oxidation states, they think I'm just going to uncross it and I can get the charge that way. Now that does work for a lot of the times, but not all of the times. Let's take a look at this example. If I do my example, chromium, and I attach it to the 2 nitrogens, and each nitrogen has a -3 charge, using my periodic table, I have a total of a -6 charge in this compound. That means then chromium has to be a +6. So when naming this, I would be writing chromium, and I'm saying that its charge was a 6, a Vi. But look what would have happened if I would have just uncrossed that. I would have thought that it was a +2. Now the reason why it happened was when chromium was a +6 and nitrogen was a -3, and we crossed those down in a crisscross fashion, we reduced it to CrN2. So that extra step is kind of hidden in there when you're trying to actually determine the oxidation states. That's why drawing things out is a sure way of determining what that oxidation state is. Okay? Let's take a look at this silver carbonate compound. I have 2 silvers, right? I have Ag2, and that's attached to a polyatomic. You have to memorize those. I know that carbonate has a -2 charge. So the total charge, is a -2 in this compound. So each silver has to have a positive charge in order to balance out that minus charge. So do you see that each silver has to be a +1, so when I add them up together, it makes that +2 to counterbalance the negative part of the compound. But when I'm naming this compound, it's going to be named as silver, and in parentheses I put a 1. I understand they add up to a +2, but if I peeked inside this compound with a microscope, if I could do that, I would notice that each silver has a +1 charge on it. All right, so that's what's being expressed in here. Not the total charge, but what each charge is on the transition metal. So that would be silver 1. Let's take a look at this last one over here with manganese. I have manganese with 2 sulfates. All right, that's a polyatomic. You have to recognize that. You have to know that they're each a -2 charge to get a total of a -4. So manganese, to balance that out, has to be a +4. So that would be manganese 4 as starting to write or starting to name that compound. As you can see that in order to determine the oxidation state of these compounds, I had to look at the negative part of the compound. Because the negative part of the compound, I could get this information from the periodic table. I knew what charged chlorine was. Or I have the polyatomics memorized, so I could use that sort of like a detective in order to determine the oxidation state, the charge of the transition metal. Now these take practice, and usually half the class catches on really good, and other half are struggling. So when we go and we practice, make sure the ones that are understanding help the ones that are struggling. But this is something that's important in the next video when I show you how to name compounds with transition metals, because this is the extra step that all transition metals need to have because they're crazy, so they need this extra work. So good luck, and let's work together as a group.